The 72 million galaxy baseline. The European Space Agency's Euclid telescope has mapped 72 million galaxies in a single sweep, producing a dataset 30 times larger than its baseline commissioning phase. This is not a gallery of deep space photography. It is a high-resolution structural scan of the dark matter scaffolding that dictates where every star in the local universe can actually exist. We are looking at the primary architectural blueprints of the cosmos, and the sheer density of this data indicates that our current distribution models are missing significant mass variables. This specific mapping project is the only viable method for visualizing the invisible framework that holds galaxies together. These raw telemetry sets reveal a much noisier structural reality than the smooth simulations we have used for decades. The mechanism of gravitational lensing. Gravitational lenses occur when a massive foreground cluster acts as a natural optical lens, bending light from objects behind it into distorted arcs. By measuring the specific geometric shearing of these 72 million light sources, Euclid can calculate the exact mass of the invisible dark matter sitting in between. It is the only way to measure gravity without seeing the physical source. Think of it as observing the wind by watching the movement of wheat. We are measuring the warp, not the light itself. But identifying these 10,000 new lenses requires a level of precision that challenges our current processing hardware. The failure of automated detection. You might expect neural networks to handle this pattern recognition, but even the most advanced computer vision models currently fail when distinguishing a genuine Einstein ring from a simple spiral galaxy or sensor artifacts. The geometric variations in these lenses are too irregular for standard classification algorithms, which frequently flag false positives in high-density fields. In a calculated pivot, the European Space Agency has offloaded the identification of these 10,000 potential lenses to a global network of volunteers. This citizen science effort is not a marketing stunt. It is a necessary engineering workaround, because the human eye remains more efficient at spotting the subtle asymmetric shearing of light that indicates a dark matter filament. This human-in-the-loop requirement is the primary bottleneck in the mission's data pipeline. The 75 Milli-Arcsecond constraint. While the marketing focuses on the 30-fold increase in dataset size, the real engineering achievement is the telescope's pointing accuracy. Euclid maintains a stable orientation with a deviation of less than 75 milli-arcseconds over long exposures. Without this extreme mechanical stability, the weak lensing signals would be lost to motion blur, rendering the entire dark matter map scientifically useless. It is a masterclass in attitude control engineering that far exceeds the requirements of previous survey missions. This level of precision is what allows us to identify the subtle clumping of dark matter that older telescopes simply smeared away. These clumping patterns are the first real evidence that the standard model of cosmology might be incomplete. The signal under the noise. This 2026 Euclid data release proves that our reliance on automated black box discovery has reached a hard physical limit. By integrating 10,000 gravitational lenses into a single model, we are seeing that dark matter is significantly clumpier than the fluid-like distribution predicted in 2020. This suggests the early universe had different thermal constraints than our standard lambda-cooled dark matter model currently allows. For engineers and researchers, this means the quality of human intuition in data filtering is now the primary constraint on astronomical progress, rather than raw sensor sensitivity. If these clumping patterns are verified, the standard model of cosmology is due for a hardware-level rewrite. This shift will force a total recalibration of how we calculate the expansion rate of the universe. Watch the upcoming data drop in November for the first formal attempt to reconcile these clumping anomalies with the Hubble constant tension. Subscribe for more.